Right, so this is your code, everyone. If you've taken, then let's discuss. So for today, I'll probably discuss about 3 questions here. The rest you can try. Alright, for this chapter, right, entropy calculation we probably won't focus too much. It is a bit more useful. Again, when we study entropy, it's actually more useful for when you study cycle in the later chapter. Alright, the actual calculation part here, you know enough. Alright, so here, this tutorial, just like previous tutorial, we also split it into 2 parts. We have the first part, which is more focused on the second law theory part, and then the second part, which is on entropy. So I will look at the first part. I'll choose probably 2 questions here. Then the entropy one question. Then yeah, that's probably about all the time that we have for this. Okay, so here we look at problem 4 first. Problem 4 is actually a more Okay, so problem 4 is actually more of a. So many people. Okay, so this is actually a more zoom in version of refrigerator. So in here we have a quick look here, which means what I want to say is this will be a more simplified version. In your chapter 9, which is your final chapter, then you will see exactly how we analyze this thing. But here you can have a basically a sneak peek of it now. Alright, so here let's read the question. So R134A, so we start with R134A. So this is the refrigerant, so don't refer to the wrong table. Enters the condenser of a residential heat pump at 800 kilopascal and 35 degrees Celsius. So it enters the heat pump at this pressure. Actually the condenser of a heat pump, no, correct. So this is what it is we are referring to. Let's call this 1. And we know, and the mass flow rate is 0.018 kilogram per second. And it leaves at 800 kilopascal as a saturated liquid. So this is also more or less what you learned in your lab as well. These are the things that you measure in your lab. Right? Same thing. We measure what's the temperature and pressure entering the condenser, and then what's the pressure leaving the condenser. And of course in the lab you measure temperature as well. Here we just tell you that this is a saturated liquid. So theoretically most of the time this is the case that we assume. Again, you will learn this in the final chapter. So if the compressor consumes 1.2 kilowatt of power, so this is 1.2 kilowatt. So let's call this 2 to make things easier for us. You need to determine the COP of the heat pump and also the rate of heat absorption from the outside air. So there are 2 things that you need to determine here. Of course, so far what you learned for this, right, it basically looks something like this. So this is the heat pump, and you are taking heat from the TL, and you are taking heat from the TH. Right, so this is actually what you learned so far. But now, like I said, we are zooming in, and we try to have a closer look at this thing. So for A, you need to find the heat COP of the heat pump. So for a heat pump, what is the COP equation? So what is expected from a heat pump would be the QH, right? This is the output. While the input that you are putting in will be work in. So this is how you can find the COP, right? Of course, general equation. So work in here is given to you. This is 1.2 kilowatt. The question here will be, how do we find QH? So how do we find QH? Okay, so even if you use that, you don't have any information. You don't have QL here, you don't have QH here, you don't have TH, you also don't have PL. And also that relation is only for reverse Carnot cycle or reversible process. So if the question doesn't really mention anything related to that, you actually cannot use that. So anyway, yeah, all four of them are unknowns here, so you cannot use those. You don't have enough information. Why? Because you learned this in the lab. Yeah, actually I was going to say that. So the easiest way, the fastest way here is, yeah, you learn this in the lab. The energy change here is just the enthalpy, which is this one, right? M dot. You can write H1 minus H2, H2 minus H1 doesn't matter. But of course, one will give you negative value, one will give you positive value. But here we know that QH is an out. We just keep everything as positive. So in general, in a cycle, you will know clearly which one is positive, which one is negative, because the same thing won't work the other way around. So mostly we just keep it as a positive value. So this is a H1 minus H2. Now the real reason why this is just M1, why this is just a change in the enthalpy, is this. What is this thing? This is a condenser, right? So what system is a condenser? Open system. Condenser. You have flow flowing in and out. We are only looking at condenser here. So if you write the whole thing, if you want, you can write. Okay, I was just skip KE and PE because those things we usually just assume they are negligible because not significant. So if you just look at this whole thing, right? What is the function of a condenser? The condenser is to reject heat. So this one we cancel off. Condenser is to reject heat. And for work itself, there shouldn't be any work to a condenser because it's just a heat exchanger. So you cancel this one off. So if you move them around, it just Q out equals to M dot H1 minus H2. So it's the exact same equation. So this is actually how we arrive at this. But of course, lab will just tell you it's a change in enthalpy. It's too much work. Your lab cannot finish in 2 hours. Okay, so we have shown that so QH is Q out. So QH is just the change in enthalpy. So from here then things become easier, right? Because you know that P1 is 800 kilopascal. You know T1 is 35 degrees Celsius. This is a superheated state. So from here you can get H1. Then you also know that P2 is 800 kilopascal, saturated liquid. So from here you can get H2. Is it just me or does it look a bit low res today? I complain one night. They changed the setting. Okay, so from here, then you get H1, you get H2. Mass flow rate is given by the question. Then you can find the COP. So B is the rate of heat absorption. So what actually is the rate of heat absorption? Power. I mean it is power, not wrong. So rate of heat absorption is pretty much QL, right? Because you are absorbing heat from the outside air here. Then you are rejecting heat over here. So rate of heat adjustment is actually QL. And so here, very straightforward. We know that energy in general equals to energy out. So QL plus work in is equals to QH. So you have the value for both Q in and QH. Then from here you can get QL. actually not just lower resolution, right? The whole thing also smaller, right? Usually it's bigger, right? So I noticed I wrote very big here, but then it was very small, right? See the okay, so is everyone done with this? Yes, then I'll move on to the next slide, sorry, next question. Okay, so the next one that I want to discuss is actually question 5. Let me bring it over to the next. Let's get some space. Okay, this one is sort of interesting question because we have two things here. So let's just read the question first. A Carnot heat engine receives heat from a reservoir at 900 degrees Celsius at a rate of 800 kilojoule per minute and rejects the waste heat to the ambient air at 27 degrees Celsius. The entire work output of the heat engine is used to drive a refrigerator that removes heat from the refrigerator space at -5 degrees Celsius and transfers it to the same ambient air at 27 degrees Celsius. So in this case, you have both heat engine as well as refrigerator. So let's draw the second law diagram here first and see how it looks like. Okay, so this Carnot heat engine. Now Carnot heat engine is a key term because the moment the question says Carnot heat engine, you know that this is a Carnot heat engine. Like it runs on the Carnot cycle, the most ideal cycle. So it takes in heat from, so the TH here in this case is 900 degrees Celsius. It's too small, let's make it bigger. And so we take it in here, this is a heat engine. And it rejects it to a 27 degrees Celsius. So this is, okay. Then the work net output. So let's call this, so this work net out. And here, this is QH, 800 kilojoule per minute. So this entire work net output will go to a refrigerator, which removes heat from a refrigerator space at -5 degrees Celsius and transfer it to the same ambient air. So here I will use the blue one to represent the refrigerator, but of course in the exam you cannot really do this, so maybe you define it properly, yeah, like this. So let's say here I just say that this is for the heat engine, the other one is for the refrigerator. Okay, so meaning here you also have technically speaking a heat engine here. And here this is QL. Okay, so this is roughly how it looks like. Make sense to you? Anyone that cannot understand this diagram? Okay, so now this diagram also represents what I told you in the class, whereby I said I don't actually like to use the term QL and QH because you can see here the QL and the QH for heat engine and also refrigerator don't have the same meaning. Because for the refrigerator, QL is actually QE, while QH is Q out. For the heat engine, QH is QE, while the QL is Q out. Because the H and L basically only refers to where is the high temperature and where the low temperature is. and which in this case they are the opposite of each other. Okay, but yeah, you just need to remember that's the definition for high and low. So don't confuse between in and out. The direction you need to be clear on. Alright, so this is roughly how the whole process looks like. Then we look at the question. So you need to determine the maximum rate of heat removal from the refrigerated space. So meaning we are looking for QL maximum. Okay, let's call it max. This is what we are looking for. So, in order, maybe we go one by one first. Now the only information that you have here is QH for the heat engine. So very obviously you need to use the heat engine in order to find the information for refrigerator, right? So we start from the heat engine first. The link between them will be that the work into the refrigerator is equal to the work net out of the heat engine. Right, so meaning the first step that you should do is to find out what is the work net out. So what else do we know about the heat engine? Ambient is 27 degrees Celsius. So what else do we know about heat engine? One more, like I said, keyword, the very first sentence. It is a Carnot heat engine. So if this is a Carnot heat engine, meaning, so we have a Carnot heat engine. So this will give you the maximum thermal efficiency. And how do you find the maximum thermal efficiency? It's based on, so like I said, don't memorize. The general equation is basically just this, or QH, whichever one. Then this is equal to 1 minus QL over QH. So since this is the Carnot version, maybe let me move this down. Since this is the Carnot heat engine, we also know that, then you can use QH over QL equals to TH over TL, or the other way around. So this is TL over TH. So here you sub in 300 Kelvin, here and here you sub in 1173 Kelvin. And from here you can get the maximum network output from the heat engine. So one more thing that I didn't mention. So from the question, the answer, you can see that I actually leave the answer in terms of kilojoule per minute. So like, usually we will convert the unit to unit SI or whatever, right? Now, if the question doesn't really mention anything about what kind of unit you need it to be, and also like in this case, you actually only have one unit to deal with, which is kilojoule per minute, because other than that, we didn't give you other value. So in this case, you can actually just maintain it as kilojoule per minute. You don't need to waste too much time in converting. Of course, if your question have two or three different type of unit, then you still need to convert them to one same one anyway. Then of course, then you convert it to kilowatt or kilojoule per second. But otherwise, in this case, you only have 1 kilojoule per minute. It's okay for you to just leave it in kilojoule per minute. Easier to calculate also. Okay, so far everyone can understand what we are doing here. So from here you can get the network output and so we bring back this, right? We know that this is the case. So now how do we relate QL with work in this case? So again, we know that COP of a refrigerator is QL over work in, right? I will skip the R. This is what we know. And the question asks for the maximum rate of heat removal, which also means that we are still doing the same thing. So for maximum heat removal, the R must be the reversible Carnot cycle R. So it must be a fully reversible refrigerator, basically that. Okay, so which means that we can again do the same thing. We know that this equation so there is a version here which I forgot what's the equation. QH over Q. And we do the same thing, TH over TL minus 1. So again, this time you need to be careful. TH in this case will be 300 Kelvin, while your TL will be 268. So then you can get QL value. So clear? Any question here? If not, then we can quickly finish up part B. So part B essentially asks for the total heat rejection. So what we are looking for is actually QLHE plus QHR. So basically, this is very straightforward. This is just QHE minus work net out. And QHR is just QLR plus work in. So that's all. So this way you can find how much total heat is being rejected to the ambient air as asked by the question. Just now I asked them things that I teach this morning. They remember that they have learned some of them, or no one remember. Do you guys remember?
Not that much. The things that we learned today or
Like this morning.
but a lot of new terms are so
But not entropy. Entropy you learn in thermo, right? But what I was like, just like the isentropic and the isentropic equation, all those actually apply to it. But a bit lah, not much lah. Because I was preparing like then was like, you guys haven't learned the more, so you guys will be the most thing. Because last time actually started together one. The more is second year, second semester last time. Then because of the pandemic, then I stopped it. Actually the stopped shooting that
but if both subjects together, I think it's very stressful.
yeah, because usually after exam then what's your result? Alright, so if anyone got no issue with this, we look at one entropy question now. The one that I choose to look at, you don't really need all those equations one. Okay, we look at problem 8. So once again, we are looking at R134A here. So like I said again, always, whenever you are solving this type of question, always determine whether what kind of question you are looking at first, and also what substance that you are dealing with. So here, the diagram is, I didn't take the diagram, but the diagram is here. So the diagram here actually also shows that it is a piston cylinder device. So what we have here is a piston cylinder device, which also means that this is a closed system. And we are dealing with R134A. So need to be clear what you're dealing with here. Okay, maybe we draw a bit, whatever it is, actually not too important. Okay, so we know that initially the pressure is 320 kilopascal. The temperature is 40 degrees Celsius. So it undergoes an isothermal process in a closed system until its quality is 45%. So we know that X2 is 0.45. So A, draw TS diagram for this process. Technically speaking, you can't draw it right away because you don't know what is the initial state. Right? So meaning, even though question didn't really ask you to solve anything, what you need to do here first is that you need to check what is the initial phase here first. Based on pressure equals to 320 kilopascal and temperature equals to 40 degrees Celsius. Can someone quickly check this and tell me what state it is? This is R1348, so don't look at the water table. Both of them, see which one you can understand better. Well, better. Actually, just that table just not can give you answer. If you have 0.32 megapascal there.
The closest one is
Equation. No, I don't need any value here. This one, what state is this? Or what?
superheated.
Okay, so now, so initial state is a superheated state, right? Let's see. So initial state is a superheated vapor state for R1348. So because A, we need to draw TS diagram. So if you do not know what is the state, you can't draw the TS diagram, right? So when you are drawing water and R1348, don't forget the saturated line. Then we know that initially it is a superheated state, so it should be somewhere here. And you know that final state is 45% quality, so which means that actually, yeah, it will end as a mixture, so it is this way. So the diagram will go this way. So even though, okay, my line is not very straight, but it should be a horizontal straight line now to the left, because this is an isothermal process. Temperature doesn't change. Alright, so even though question doesn't really say anything about what process is taking place here, more or less you should know that this is a cooling process. Right, because entropy is reducing. So you can also pretend that you don't know anything at this point. Then we try to solve it in B first. So this is your A. So B, on per unit basis, determine how much work and heat transfer are required. So you need to determine both the work and heat that occurs in this state, right? So this is a closed system. Easiest way, you start with Q minus W equals to, okay, sorry, the small letter version, because we are looking for in terms of per unit basis. Delta U. So U2 minus U1. Okay, again, if you can know clearly what is the Q in, Q out, work in, work out, what are the Q in, Q out, work in, work out, you can expand the whole equation and then can solve accordingly. But here, we don't do that first. Let's pretend we don't know anything here. Okay, so what do we have here? We need to figure out this. We also need to figure out this. We can find out U2. Can we? We can, right? We can also find out U1. So for P, so let's write them out first. So for state 1, we know this. So based on this, just now you have also determined for me this is a superheated vapor or superheated R1348, superheated refrigerant. So from the superheated table, you can get U1. Second state, we know that T2 is equal to T1. And x2 is 0.45. So from here, you can also get U2. Or maybe, I'll get the answer. So if you read the table, this should be the value that you get. Okay, now, so for most of you, I will expect you to at least be able to reach this point now. Okay?
So that one table, right?
Yeah.
The x2. So
S2 from table? No, S2 is question.
oh yeah. So it's given. So we find the value of u2 from the table. Is it?
You need to find UF and UFG. Then you use the S2 to calculate U2. Because it's a mixture. Okay, so again, for most of you, this is probably where you will stop. Or at least, my expectation is at least you can do until this point now. Alright, but now we still have two variables, and the two variables are actually what the question is asking for, which is Q and W. So you need a way to find out these two things. What can we do here? Can you recall anything from this morning? What is the area under the graph of a TS diagram represent? It's heat transfer, right? So meaning you can actually find Q in this case. And since this is an isothermal process, actually it doesn't matter. But yeah, so here this area under the graph will be the Q. So again, we still pretend that we don't know which direction this Q is going first. So this should be S2 minus S1. Multiply by T. 1 or 2. Doesn't matter. T naught. Okay, so this is the same equation as what you learned this morning. This morning we learned that isothermal process, then delta S equals to Q. It was capital Q over T, right? So same thing here. We just move T naught. So we just move the T over. That is the equation. So which means we still need to find two more things from the table. You need to find out what is S1. You need to find out what is S2. Oh, sorry, I accidentally wrote extra terms. Just T. Okay, so just from this diagram, you don't actually need to, you don't even actually need to check the table to know this. This will actually give you a negative value. Right, because if you look at the graph, S2 is definitely a smaller value compared to S1, which means this Q will be a negative value. You will get a Q out in this case. So if you sub this Q out value, so the Q out is, so now if you are using this complete Q minus W equation here, okay, so this original equation, then you need to sub in the entire value including with the negative value in. So meaning here your equation becomes negative minus W equals to U2 minus U1. Something like that. So when you solve this, the work value will give you a positive value, which represents that this is a work out equation, work out term. And again, like I told you, if your equation only have one Q, one W, it definitely will be one in, one out. You cannot be both in or both out for a closed system. Okay, so they will always be the opposite of each other. Sorry, then this will be both in. What am I saying? Which means this will be a negative value also. Yes. So of course, now let's say if initially you wrote this equation directly, okay, so let's say if this is what you wrote initially, and then you speculate. So you speculate that this is zero, and this is 0. So you will end up with Q out plus work in equals to U2 minus U1, right? So if you write this equation, right, then this Q value, when you sub in here, you should sub in the positive value because the negative here is already here. And then your work in, you should get a positive value because of that. So these are just two things. So this one is you define the direction right from the start. This, when you use this, is when you don't know what is the direction. If the bottom one confuses you, then forget about it. Then follow the standard convention. Okay, so we are left with 5 minutes. This is where I will stop. Do you have any questions that you want to ask about this? Any part that you don't understand?
DH 出来那个之前会